Hi and good evening. I'll just start in a while, okay? I'll just share my screen and we will start.
Good evening, sir.
Yeah, so hello, good evening and welcome to the final session on our tutorial session on power electronics with wide band gap devices, right? So
Good evening.
from the last class itself, we have been seeing a few questions and previous year assignment problems on from different topics, right? So I think in the last class we covered questions on motor drives, then renewable energy sources, and also we saw a few questions on PCB design, right? And finally, we came to questions on power density, if you remember. All right. So we will continue with that today. Okay. So yeah, the last question we saw was this: what is the relationship between inductance and switching frequency in a buck converter? This particular question, right? So this is what we saw, and we saw that it was inversely proportional. All right. So this was the last question we saw. Okay. Yeah, and by the way, I think I missed out on uploading this particular slide in the Google Drive. So once today's session is complete, I will upload both this and today's slides. Okay. So today we will just keep it in continuation with the original slides. All right. So yeah, we will go ahead with the next question. Okay. So most of these questions are simpler, but we'll just discuss it for the benefit of your exams. Okay. So which of the following is not a type of switching loss? So by the way, is my screen shared? Yeah. Okay. So the options. Yeah. So the options you get are conduction loss, turn off loss, reverse recovery loss, and gate charge loss. So what is the answer for this? For question number 5. So the answer is highlighted. So which of the following is not a type of switching loss? So turn off loss comes under switching loss, right? And turn on loss will also come under switching loss. Reverse recovery happens once during every switching of the device, right? When it stops conducting in the reverse direction, reverse recovery loss happens for the antiparallel diode of the device, right? So I hope my voice is also audible. Yeah. Okay. And gate charge loss also happens due to switching. So the correct answer would be this, that is conduction loss. Okay. Okay, fine. And so the next question would be, what is a major challenge increasing switching frequency? Increased conduction loss, higher switching loss, and thermal issues, difficulty in controlling voltage. Okay, so which of the following is the answer for question number 6?
B.
Sorry,
B.
B. Right. So the answer would be, as switching frequency increases, your switching losses will increase because your switching losses is proportional to your switching frequency. This is something we have seen multiple times, right? So if your losses increase, then obviously the junction temperature of the die increases. Therefore, you will face thermal issues. So the answer is B, correct. Okay, fine. So can I move ahead to the next question?
Yes, sir.
Okay. So the next question would be, it is on packaging. Which packaging innovation improves or helps in improving thermal performance by maintaining size reductions? Control package. CSP package. Chip package. So what is the answer for this question? Okay. So what is the answer for this particular question? Question number 7. Which packaging innovation helps in improving thermal performance while maintaining size reduction? Hot rod, power CSP, uh, wafer scale chip packaging, or flip chip package? Anyone remembers from your lecture slides? The answer is A, hot rod package. Okay. So I'll just show you how these packages look. Okay. So probably if you can see it, you might remember hot rod package, right? Yeah, hot rod QFN package. Yeah, you can see over here, hot rods keep the die cool. Okay, so the answer to have a compact package and have better heat dissipation is hot rod package. So generally what happens is if you go for smaller and smaller packaging, thermal dissipation becomes an issue. That is, how do you effectively take out the heat, right? So an effective way to do so is this hot rod package. Okay, you can see other packages also. So hot rod package, then so in hot rod package, you have these, what to tell, these are these rods, okay, which help in thermal dissipation, right? And you have power CSP package, which is used for ICs, okay, something like this, okay. And you have uh, WSCP package, wafer scale chip packaging, right? WCSP. Yeah, something like this. So this is called as a ball grid array. Okay, you have an array of small balls. Okay, which can be directly soldered onto the PCB. Right? You will use solder balls to put these on the PCB. So this is another option: wafer chip scale packaging and wafer level chip scale package. That's the definition. And finally, you have flip chip package. Okay. So flip chip as in like you kind of directly mount the chip. Yeah, something like this. Okay. That is you directly kind of place the die and cure it. Okay. You will put some material and you will allow it some time so that the material gets cured. Okay. So, but anyway, for the question regarding the thermal dissipation, which package is most suitable? The answer is hot rod package. Hot rod package. Okay. This. Yeah. So the answer is this. Okay. Which packaging innovation helps in improving thermal performance? It is hot rod package. Okay. So we will move on to the next question, right? Um, which of the following best describes the trade-off between RDS on and switching losses in MOSFETs? Lower RDS on decrease the switching losses. So which is the answer for question number 8? So which of the following best describes the trade-off between RDS on and switching losses in MOSFET? So trade-off as in like they may not be directly related, but as a ballpark figure, like based on the data sheet that you might have seen, right? So what is the general figure? If you go for lower RDS on, what happens? If you go for higher RDS on, what happens? Okay. So trade-off as in like it's not a direct relationship, but indirectly is there some relationship based on what you have encountered in real life, right? So what is the answer for this question? Okay. So the answer for this question, I'll just check if I'm there. Okay. So the answer for this question is answer B. As a ballpark figure, right? As a ballpark figure, generally you will see that switching losses and conduction losses are kind of complementary. Okay. That is, if conduction loss is high, you will see that the switching loss is lesser and vice versa. Okay. So if you have lower RDS on, you're going to have lesser conduction loss. And if it is lesser conduction loss, generally you will see that the switching loss is higher. Okay. But ideally, if you want to ask what is the relationship, right? There is no such relationship between directly your RDS on and the switching loss. Okay. Just as a ballpark figure, we are telling its answer B. That is, if conduction loss is high, switching loss will be lesser and vice versa. But directly, as such, there is no relation. Okay. RDS on does not affect switching loss directly. Okay. Okay. So can I move on to the next set of questions? I mean, can I move on to the next question? Is this fine so far? Okay, fine. Just a second. So the next question would be, is reducing loop inductance important for improving power density? Yeah. So can you tell which is the answer for this question? Why is reducing loop inductance important? So why is reducing loop inductance important for improving power density? Why? So if you reduce loop inductance, what will happen? Would it increase the switching frequency? Would it reduce the voltage stress on the devices? Reduces the size of the heatsink and increases the power output. So anyone knows the correct answer?
A. Option.
Option A. So why would you tell it?
Inverse proportion, sir. To switching frequency.
Okay, so how does it directly affect? Means like if you have smaller loop inductance, right? Then what would happen? How does it directly affect? So
Actually, in the power density, it will be heat sink only will come producer side.
okay, heat sink is there, fine. But like, how does it directly translate to your loop inductance? Loop inductance will not affect your heat sink, right? Like loop inductance, whether let's say I have two cases, I have 5 nanohenry loop inductance, 10 nanohenry loop inductance. How would it affect the size of my heat sink? Right? So sizing of our heat sink we have seen earlier also, it is based on the thermal resistance R theta. That is based on the power loss that is happening in the device. Right? So that is how you decide the heat sink. So whatever is the power loss happening in the device, you have to remove away that heat. That is how we have seen the heat sink design and all. So how would loop inductance translates directly to size of heat sink? Okay, so this is actually a very conceptual, very good question, I would tell. Okay, so I'll just discuss this. So what is the okay? So let's see the turn off transition for a device. Okay, so turn off transition for a device as in like see. Let's say this is my VGS. Okay, and my VGS was high. Okay, plus 15 volts. Let's say it was high, and at this point what I do is I withdraw the gate pulses. Okay. The gate pulses were high till this point. At this point, I make the gate pulses 0. Right? This is what I have done. So what happens? You will remember, I think, that what would happen? Let's go back to the circuit over here. Your circuit looks something like so what is the circuit? What is the circuit we have drawn over here?
Repeating.
Yeah. So it's a typical half-bridge circuit. Okay. So this is S1, S2. Let's call this is RG. This is also RG. Okay. This is VG1. This is VG2. Okay. And this is your ground. Okay. And this is your switching node. Okay. I have a constant current that flows in this direction, which we will call it as IL. Okay. So now the point is, let's assume we are talking about the bottom device, right? So we are talking about the bottom device, the voltage between gate to source is VGS2, which is what we have drawn. Okay. So the bottom device was on all this while. Okay. Bottom device was on and then we have turned it off. Okay. So we have turned off the bottom device. And okay, so I will, for simplicity, what I will do is let's assume we were talking about the top device. Okay. So not the bottom device. We will consider the top device, VGS1. Okay. We were talking about the top device, VGS1. Okay. So now we are turning off the top device. So initially what was happening? Initially my top device was conducting, as in like the current direction was something like this. Agreed? This was my current direction initially. Okay. This is how the current was flowing. Okay. So let's draw the other state variables as well. So my device was conducting a constant current of IL. All right. So the device was conducting a constant current of IL. This is IDS1. Okay. Top device current. The device was conducting a constant current of IL. Okay. And what about my VDS? What would be my VDS till this point? Not exactly zero. It will be some I into R drop, but we will practically assume it is very low. All right.
Yes.
So somewhere over here. Okay. So now what happened? We turned off our top device the top device gate pulse. Okay. And we pretty well know that the top side gate can be approximated as something like you have a source over here. Okay. So you just made the source go to negative. Okay. Plus 15. From plus 15, it went to minus 5 volts. All right. So we have minus 5 volts over here. We have RG. And then there is the gate capacitance. Okay. We saw that it can be called as CISS. Across it, you are having your VGS. Okay. So once this is known, how would your VGS decrease? What would be the profile of decrease of my VGS? It would be 1 minus e power minus t by tau, right? Like that is how your gate voltage would decrease. All right. I'm sorry. It would be e power minus t by tau, right? So your VGS would decrease something like whatever is your VEE into e power minus t by tau, where tau is equal to RG. All right. So let's assume that gate decreases linearly. Okay. So it will come till this point. It has decreased. Then Do you remember, like, there was something called as Miller region in the gate dynamics? Okay, so let's try to recollect. See, your entire current was flowing through top device. Okay, the device current direction is as shown over here. Okay, in the red line, right? That is over here. That is how your device current is flowing, right? So now what happened is you want to turn off S1. Okay, you want to turn off S1, which means that S2 has to carry all the current, right? Okay. So if S2 has to carry all the current, actually it is not S2 that will carry the current. It has to be the diode of S2 that will carry the current, right? That is this particular diode, right? Because the current direction is like this. So the current will go through the load, come back over here, and it has to flow through the diode. Do you agree? Do you want me to repeat, or like, do you agree till this point?
Agree.
Okay. So you want, after S1 turns off, you want the diode to carry the entire current. Okay. So when will the diode carry current? Diode can carry current only if there is no voltage across it, right? Can a diode carry current if there is a voltage like this? Can a diode carry current?
No.
No. So diode cannot carry current if the voltage is like this. Okay. So you saw that VDS1 is 0. Initially, VDS1 is 0. The voltage across this is almost equal to 0 initially, which means that voltage across S2 was VDC. Agree? Do you agree? Voltage across VDS2 was at VDC initially, right? That means S2 was off. It was blocking the entire DC bus voltage. Do you agree till this point?
Yes.
Okay. So now what should happen? You want the device S1 to turn off, and S2, what will happen? The current should be actually freewheeling through the anti-parallel diode of S2. Okay. But one thing is, the diode of S2 cannot carry current until the voltage falls, right? Until the diode voltage, the voltage across S2 falls. All right. That means that if S2 has to fall, then S1 has to start blocking the voltage. Do you agree? S1 has to start blocking the voltage. Okay. So that is why you will see that first you will reach this Miller region. This is something we studied during turn on also, right? There is a Miller region wherein what will happen is your um, voltage, right? Your drain source voltage for the top device will increase like this till VDC, and obviously for the bottom device or the voltage across the freewheeling device will fall complementarily. Do you agree till this point?
Yes, sir.
Are you able to relate to what we studied during the turn on? During turn on, we saw that first there will be current rise and then there will be voltage fall, right? Over here, it's the opposite. First, there will be voltage rise and then current will fall. Okay. So you understand that the diode cannot conduct until the voltage changes, right? Until the voltage across S2 becomes 0, right? That is, we have drawn VDS2 also. Until the diode voltage approaches 0, the diode cannot conduct. So till that point, the device will continue to carry current. Okay, the device will continue to carry current. And after this happens, right? After this happens, Once the voltage has fallen, only after that your current will fall to zero. Is this agreed by all of you?
Yes.
Like
Yes, sir.
Anandi, are you able to understand this? How this has happened?
Yes, sir.
Yes.
So this is the opposite of your turn on. Okay. So so this is the opposite phenomenon of turn on. Okay. So first you see that there is first you will see that there is voltage rise and then only you will see current falling through the device. Okay. So we were seeing that there is current rise time, voltage fall time. Here it is opposite. Here first there will be voltage rise time during turn off and then there will be current fall time. Do you understand this till this point? So in this also we studied three intervals. That is during the turn on we studied three intervals. One was the turn on delay time, then current rise time and then voltage fall time. Okay. Here also there are three intervals, that is voltage, the turn off delay time, then voltage rise time and then current fall time. Okay. So here also you have three intervals, right? That is, this is called T turn on delay time, turn off delay time, TD of voltage rise time and then current fall time. Okay. Okay, so I hope you understand till this point, right? So opposite phenomenon of turn on. So first there will be turn off delay time, then voltage rise time, and then current fall time. Do you understand till this point? Like we can go ahead only if you understand why this is happening and all. You please give 2 minutes over here. Initially, the VGS1, right? Initially the device was on. The current direction was something like this as indicated in green on the right hand side in the picture, right? That is, it was like this. Okay. Then what happened? I wanted to turn off the device. So you can see the yellow line, that is the pulses from the microcontroller are turned off at this instant. Then what will happen? It's an RC network eventually, right? So initially there was 15 volts. Now you made 15 to -5, right? Let's assume the gate voltage is plus 15 and -5, right? The gate voltage is plus 15 -5. That is our gate voltage. Okay. So you understand that we made plus 15 to -5. So if you have made it -5, right? That is, you want to discharge the capacitor CISS, right? It's an RC circuit. If you want to discharge, you will know that for an RC circuit where you want to discharge something, the dynamic is VE into minus e power minus t by tau. That is, you should see a dynamic something like this, right? But we will assume that this fall is linear for our modeling purposes. Okay. So what happens? Your gate voltage starts to fall. Your gate voltage. So your gate voltage starts to fall. So once it starts to fall, initially you understand that, see, if I want to turn off S1, right? If I want to turn off S1, it means that the current IL has to be carried by the freewheeling diode of S2, right? That is through this diode as indicated in the dark blue line, right? That current will flow through the antiparallel diode of S2. If the diode has to conduct, right, there cannot be any voltage across the diode. That is the basic rule for diode to conduct. Diode cannot conduct if there is voltage across it, right? Diode will not become forward biased. So you understand that first, for the current to get transferred, first there has to be change in the voltage. That is why we encounter first Miller voltage during turn off. It is the opposite phenomenon of turn on. First, there will be Miller region, right? So during Miller region, what will happen? Initially, switch S1 was on, therefore there was no voltage across it as indicated over here, and switch S2 was off, therefore entire VDC or the DC bus voltage was appearing across S2. Okay. Now what will happen during the Miller region? Your voltages will kind of have to interchange. That is, S1 should start blocking voltage, S2 should stop blocking voltage. So that is why during Miller region, you see VDS2 will fall, and as VDS2 falls, VDS1 will rise as indicated in the blue line. Okay. Once the voltage has transferred and the voltage across the diode has become zero, right, as VDS2 goes to zero, then what will happen is your current can start to fall as indicated in the green line, right? So first you will encounter turn off delay time, then voltage rise time, and then current fall time. Okay. So is this clear? Is this fine?
Yes, sir.
Oh, okay. So I hope you understand, right? Like you are able to relate between turn on and turn off, I think. Okay. Okay. So now we will come back to, okay. So what is the problematic part over here as far as losses are concerned? Which is the region we should be concerned about? Let's name this A, B, C. So which is the region we should be concerned about regarding losses? Or what are the regions where you will have losses in the device? Where will you face losses in the device? S1?
Delay
Mainly
time.
B.
Huh?
Mainly B.
Mainly B.
Yeah.
Okay. Why?
Because that it will
Voltage and
take
current
turn on.
overlapping.
Okay. So voltage and current are overlapping, right? I'm talking about S1, so don't consider S2 voltage, just the blue line. Okay. This is your VDS1. Over here it is VDC. Okay. Now you tell me, where should we be concerned? Should it be only B, or is there any other region that we should be concerned about?
Now VDS one only conducting, then
Okay. So over here, what is, we will just write, no worries. Okay. So over here, what is VDS2? It is almost zero,
yes.
right? I'm sorry, what is VDS1? It is almost zero. And over here, it is IL. So V into I, right? So IL into zero is anyway zero. So no worries. During the delay time, during the turn off delay time, the power loss is zero. Okay. No worries. And what about this region? Over here, the current is IL and voltage is rising. Okay. So the power loss will also increase from 0 to what value? 0 to the final value will be VDC into IL. Okay. The power loss increases from 0 to VDC into IL. Okay. And what about the third region? In the third region, VDS1 is equal to VDC and the current is falling from IL to 0, right? It is falling from IL to 0. So the power will be what? Directly multiplication of voltage into current. So it will fall like this. Do you agree? This will be the power profile. This will be the power profile. So we should be concerned in both region B and C. Okay, because the power over here is VDC into IL. It increases during this region and it falls during this region. Right? Same way, like for turn on also, we saw the profile was like this. Do you remember? The profile was like this triangular only during turn on also. Just the timing is like voltage rise time, current fall time. Just converse of what we saw during turn on. Okay, fine. So till this point, is it fine? During turn off, what is the mechanism that we are dealing with?
Yes, sir.
Okay. So now we will come back to the question, right? So over here, we have not considered any parasitic inductances. This is just an ideal circuit, right? An ideal circuit. There are no parasitic inductances in the path. Okay. So now the question is, um, why is reducing the loop inductance important for improving power density? So we should consider loop inductances, right? So yeah, we will consider loop inductances and see what happens. Okay. So I'll just draw the same circuit once again, but this time we will draw it with the loop inductances. Okay. Okay. So do you know the names of these inductances? So this is your drain side inductance for top device LD1. Okay. And this is the source side inductance. Okay. So this is a common inductance between the gate path and the power path. So we can call this as common inductance 1. Okay. This is the source side inductance LS1. This is the drain side inductance for device 2 LD2. This is the common inductance for the gate path and power path for device 2 LCM2. And this is the source side inductance of device LS2. Do you understand the naming of these inductances?
Yes, sir.
Okay. Okay. So we will draw the equations, draw the waveforms, right? So I will just draw the voltage and current. Okay. I will not draw everything. So your IDS1, right? Your IDS1 was like this and it falls during this period and it goes to 0. Okay. This is our IDS1. And What about your VDS1? VDS, your VDS1 was, your VDS1 was initially it was very low, or we will consider it as 0. Then what would happen? We saw that VDS increases first, right? We saw that VDS increases first. Okay, so your VDS increases first, and it reaches your VDC, right? It reaches VDC at this point. Okay, and we are calling that this is your voltage rise time, TVR, and this is your current fall time. Okay, so now we have to do the same analysis when there are inductances. Okay, so now assume that this current fall is linear. Okay, that is di by dt is a constant. Okay, di by dt is a constant. Okay, so what is the current path for DS1? We saw that the current path is, okay, I will direct it draw. So it was going like this through the device, and then it goes like this. It will go to the load and all, right? So take buck converter itself. There will be load, capacitor, load and all. Okay, and then it will return back. All right. Okay. So you know that so there will be some portion of current which will go like this. So the current over here is constant, IL, right? So as my IDS1 decreases, what you will see is that IDS2 will increase. Do you agree? As IDS1 decreases, IDS2 will increase so that my total load current IL is a constant. Agreed? Is this agreed by everybody? Means like, see, in this particular period, right? In this particular period, your IDS1 is decreasing. That is, the top device current is decreasing. As the top device current decreases, what will happen to the bottom device current? Bottom device current should increase because the total current is a constant number, right? This particular current is constant at IL. Okay.
Okay, sir.
Not okay means like, are you understanding? Like, as total current is constant, the if one device current decreases, the other current has to increase. Okay. So that is why you will see that during this period itself, the bottom device will slowly start to conduct the current. Some current will flow like this, right? Okay. So I think this is till this point it is fine. Okay. So now what is your VDS1? Your VDS1 is the voltage across this to this, right? Between the drain terminal and the source terminal. Okay. So yeah, this is your VDS1, right? So when there is a di by dt, right, during this particular interval, right, during the current fall interval, right? When there is a di by dt, you cannot ignore these parasitic inductances. Okay. So what will happen to your VDS1? Can you tell me the expression for VDS1? Just tell me KVL expression.
across the inductor, LCM voltage, LSM voltage, ADS.
Correct. Correct. So your VDS1 would be your, where do I write? Okay, just a second. I'll just erase these off. Okay. And we can write it over here. So VDS1, right, can be written as what? VDC minus LD1 di by dt minus LCM di by dt minus LS1 di by dt, right? Then
LD.
minus, then whatever is the correct. Minus LD2 di by dt. So I should write this is di1 by dt everywhere, and this will be di2 by dt, right? Minus LCM di2 by dt minus LS2 into di2 by dt. Just KVL equation I have written. Okay. Fine. Okay. So during this period, right? So, okay. So I will even simplify this further. So this is going to be minus VDS2. Okay. So this is going to be what? And so, okay, just a second. During this period, your VDS2 is what? Your VDS2 is has decreased almost to zero, right? I can take for practical purposes that VDS2 is almost zero. Okay, fine. So what is my VDS1? Therefore, VDS1 is basically VDC minus LD1 plus LCM1 plus LS1 dA1 by dt minus LD2 plus LCM2 plus LS2 di2 by dt, right? VDS2 is zero almost. Okay. So this is the expression that we get for VDS1. Okay. So now you tell me what is di1 by dt? di1 by dt is negative, right? di by dt is falling, right? It's a negative di by dt, right? Because the rate of change of current is negative. The current is falling. Okay. So minus of minus is going to be a positive number. Okay. More than VDC. Do you agree? VDS1 would go more than VDC? Is this fine? Yes. So what will happen is, practically you will see there will be a huge overshoot in voltage and there will be some second order response and all, and then it will damp out like this. Okay. So this particular voltage shoot, right? This particular voltage overshoot, where is this coming from? It is due to this particular component. Okay, that is this L di by dt component. Okay, L equivalent into di by dt. Your di by dt is negative, therefore it's a positive jump. Negative of negative is positive. Okay, so your more the parasitic inductance, more will be this overshoot. Okay, if you design it properly, the overshoot will be lesser. Okay, but if you don't design the power loop properly, you're going to see something like this. Do you understand this?
Yes, sir.
Anandi, is this fine?
Yes, sir.
Hmm. So then what is the answer for question number 9? Why is reducing loop inductance important for improving power density? So what happens
Reduces the
to the
voltage
voltage?
stress.
Correct. So the answer is this. Because your peak voltage overshoot what? So let's say your VDC is 400 volts. If you don't design properly, this voltage can go like more than 600 volts. Let's say your device itself is rated for 600 or 650 volts. Then repeatedly, if you operate like this, the device will get damaged. Okay. See, a device can carry extra transient current for some time. It's not a problem. But a device can never withstand very high voltage. Immediately it will burn. Immediately it will fail. Okay, because there will be a dielectric breakdown. Okay. If it carries extra current, then for very small time it will still withstand. Okay. But if it blocks more voltage, then there will be a dielectric breakdown. Okay. So the answer is, if you don't design the power loop properly, you're going to have very high voltage overshoot. Okay, that increases the voltage stress of the devices. Okay, and you can also understand that if the voltage overshoot is more, the power loss will also be more, right? The power loss will also be more, V into I, right? So the power loss will also be more. Okay, so the answer is for question number 9, it is B, right? So the answer is B. Okay. And we will move on to the last question from power density. That is, which of the following techniques improves power density by reducing parasitic loop inductance? Yeah, so what is the answer for question number 10? So, which of the following techniques will help you reduce the parasitic loop inductance and thereby improve the power density? So what can you do to reduce the parasitic loop inductance? See, for reducing parasitic loop inductance, physically you need to make sure that the components are very close to each other. Okay, that is your decoupling capacitors are very close to the device. Okay, your gate resistance and your gate driver is very close to the device, and the entire power loop is very compact and very close. I mean, it should not be very far apart. Okay, that is how you reduce the parasitic loop inductance. Simple. Okay, more is the distance between two components, more will be the parasitic inductance directly. Okay, so what is the answer for this? How will you reduce the parasitic loop inductance?
Option A.
See, see that is one way to improve the power density, right? So if you 3D stack components, that is, I keep one component over that, I keep another component over that, I keep. This is one way of reducing the parasitic loop inductance. I mean, by for improving the power density. But how do I reduce the loop inductance? So we saw loop inductances like this, right? That is this, and we did not consider this. There will be loop inductances over here also, right? All of these are there due to physical connections. How will you reduce these physical connections? That is the question. So that I agree, one of them can be 3D stacking of components, but if you look at other options and tell me which can be more better, right? So the option is answer C. Okay. That is including gate drivers with switching power feds. That is, see, generally what people do is that they will have a separate gate driver IC. Okay. They will have a separate gate driver IC and there will be a gate resistor. Then you will put PCB traces to connect them with the device. Okay. Now, if you are having all of them very close, okay, if you are having all of them very close, then what can happen is your loop inductances will reduce. Okay. So it is like if I keep my gate driver IC very close to the power FET, right? Then my loop inductance will reduce the gate loop inductance, right? That is this particular loop inductance, right? In the gate side, that will reduce if we keep it very close. Now, what people did was instead of physically having a separate gate resistor, gate driver, and all, now people have started integrating them within the device. Right? You will get a power device in which gate driver is already there. So you just need to give the microcontroller pulses. Do you understand? So the gate driver IC has been realized monolithically within the power package itself. They have used some packaging techniques and they have gone with like how you manufacture ICs. Okay, you would have studied that an op amp has around 1 million BJTs, right? How do they realize BJTs? So within the chip itself, they have realized so many functionalities of the BJTs. So that's how something similar to that people have done. That is like within a MOSFET, within a power FET, people have put gate drivers inside it. Okay, so they are known as integrated gate drivers and integrated power FETs. Okay, so they are kind of integrated. And obviously, if you have it integrated within a single package, there will be absolutely very low parasitic inductance. Okay, so I think the name is in. I will show you one particular example. Integrated Navitas. This is one particular example. Okay, I think it is GAN sense. Yeah, so something like this. So you see over here, is this visible? Is this image visible? You see this. It says Gansen's half-bridge power IC, right? So it is a half-bridge circuit which has been realized inside. Okay, that is there are two devices inside itself already. You just need to connect the DC power supply. Okay, the gate driver is also there inside. You just need to give the gate pulses. You just need to give the pulses from microcontroller. Gate driver is already inside. It will convert the microcontroller pulses into -5 plus 15, whatever is required. Okay. Okay, so here it is written, right? GAN sense technology integrates two GAN FETs and driver plus control, sensing, automated protection, everything. So protection is there inside, sensing is there inside, gate driver is there inside. Two devices are there inside. It's a half bridge IC. Do you understand this?
Yes.
Yes.
Okay. So if you do like this, you will have very low parasitic inductance. That is why people are doing this. So the answer would be 10, including gate drivers within the switching power FETs. Okay. Yeah. So I think this question was very conceptual. So now I think you will understand why you should reduce loop inductance. The answer would be to basically reduce the voltage stress on the devices. Okay. Because during turn off, we saw that there will be an voltage overshoot if you consider the parasitic inductances. Just write KVL. You see that the di by dt is negative, that is di by dt is falling. So V minus L di by dt, right? So minus of minus becomes plus. So there will be an voltage overshoot. Okay. So for the second device for S2, if I ask, right, for S2, you see that the current is increasing now gradually. Okay. The current is just increasing, right? So for S2, I will not face any such issue because dA by dt is positive. So V minus L dA by dt will be lesser. Okay. So that is why you will see that during turn on for the same device for S1, right? We are seeing during turn off. So during turn on, you will see that there will be a voltage undershoot. Okay. There will not be any overshoot. Okay. I will try to open the previous one. Yeah, so this was the waveform during turn on. Okay. So during turn on, we are seeing that your VDS is something like this, right? Okay. This is during turn on. You see over here, IDS is increasing, which is positive dA by dt. If there is positive dA by dt, what will happen to VDS? VDS will be VDC minus L dA by dt. dA by dt is positive. So VDS will be what? It will be a smaller number. So you will see that practically you will see something like this. Do you understand this particular drop, right? This particular drop is equal to LDA by dt. Do you understand this during turn on? Okay.
Yes.
During
Yes,
turn
sir.
on, it will be just opposite. I think you can understand. It will be something like this. Okay. This particular drop is equal to LDA by dt. Okay, just the opposite. During turn off, you will see that there is voltage overshoot. During turn on, there will be an voltage undershoot. Okay. Fine. So these were questions on power density. Okay. So just give me a 4-minute break or 5 minutes break. I'll just come back and we will continue with questions on, I think, EMI. Yeah, I'll just see that and we'll just continue. Yeah, hi. So, thanks for hanging around. We will just continue, okay? And we have seen questions on power density. So, we still have around half an hour left. So, within that, we will try to maximize. Today being the last session, we will try to see as many problems as possible, okay? So, these will be questions on electromagnetic interference. Okay. So, these are all pretty simple problems only. So, what is the main purpose of a common mode filter in power supply designs? To increase the power supply efficiency, to attenuate common mode noise, to regulate the output voltage, provide thermal protection. So what is the answer? What is the main purpose of common mode filter? I think this is very simple. What is the purpose of a common mode filter?
Option B.
Right. So it is to attenuate the common mode noise. So the next question is, what does the damping factor? It is epsilon. Okay, I'm not able to write that exact symbol. What does a damping factor represent? Or some people also call it as zeta. So epsilon or zeta, whatever you want to call it. So represent in the design of a second order filter. A resonance frequency, rate of attenuation, quality factor, and filter bandwidth. So what does the damping factor represent? What is the answer?
Option D.
Option D, filter bandwidth. So how is it related? Okay, so we will try to derive this logically. Okay, so the point is, if you tell damping factor, right? Right. So it's your damping factor. So you have three basic elements, right, in electrical: R, L, and C. So damping is related with which element? Is it resistance, is it inductance, or is it capacitance?
Let's see.
It is related to which element? Sorry. So damping is related to which element? Okay, so let's take
Resistance.
correct. So if you have more and more resistance, what it does is it damps out, right? So it damps out stuff. So resistance is the element that's responsible for damping out stuff. So for example, if you have an LC network, right? And I have tuned my frequency of my AC supply, right? Such that they are in resonance. Okay. So then what you will see is there will be a continuous exchange of energy between L and C, right? And there will be kind of an undamped oscillation. You will see something like this, right? The current is going to be something like this. Okay. Now what happens is if I add a resistor, right? That is then what I'm doing is I'm dissipating some energy through the resistor. So this is kind of the damping element. So damping factor means it's going to be something that's related to R. Okay, fine. Okay, fine. So this is one point. Okay, this is one point. Damping factor is something that's related to R. Let's come to the next one. So what is the natural frequency of the system? Resonance frequency or natural frequency? So if I have an LC network, what is the natural frequency for a series LC network? Or if I write in terms of frequency, it is going to be 1 by 2 pi root LC, right? Do you agree?
Yes.
It is going to be, so it is in hertz. If it is in radians, it is going to be just 1 by root LC, right? It is in, if it's in radians, omega is going to be 1 by 2 pi root LC, radians per second. Okay, so you are seeing that natural frequency is no way related to resistance, or natural frequency is no way related to damping factor. Do you agree? Do you agree? Natural frequency is not related to your damping factor. Both of these are not related at all. Okay, so obviously it cannot be resonance frequency, it cannot be filter bandwidth. Do you agree with this? Damping factor is something that's proportional to resistance. Okay. And resonance frequency is something like 1 by 2 pi root LC. And by extension, bandwidth is also something related to 1 by 2 pi root LC. Therefore, it is independent of my frequency terms. Do you agree till this point?
Yes.
Okay. Okay. So let's try to recollect your control systems question, your control systems concepts. Okay. So for a second order system, right? For a second order system, you would have studied that y by s by u of s is something like some k into some term in the numerator divided by s square plus 2 epsilon omega ns plus omega n square. Have you seen this expression anywhere in your control systems?
Yes, sir.
Are you okay? So over here, what are these terms? This epsilon is your damping factor and omega n is your natural frequency or resonance frequency. Okay. So basically this damping factor is coming in the S term. All right. Okay. So this damping factor or this particular expression, right? This can also be rewritten as, if I take omega n square common, right? I can write this as 1 plus 2 epsilon by omega n into S plus 1 by omega n square. Is this correct? Omega n square has been taken common. Okay. And I will again rewrite this as omega n square into 1 plus S divided by omega n divided by 2 epsilon plus, sorry, this is a square, plus s square by omega n square. Do you agree with this? This kind of writing, this expression?
Yes, sir. Yes, sir.
Okay. So this particular expression, right? So this particular expression is something that's related to your quality factor. I'm not going too much into this due to lack of time and all. Okay. So the relationship, right? It's epsilon is equal to 1 by 2q. Okay. Due to lack of time, I'm not going in this. Where did I come in? So the expression is epsilon is equal to 1 by 2q. Okay. That is your damping factor is inversely proportional to your quality factor. Okay. So yeah, so the answer is this. Your damping factor represents your quality factor. Okay. Please, you can refer to control systems concepts. Okay. We want to cover more problems, therefore I'm not going into this, but yeah, you can refer to control systems concepts. Okay. Fine. Just hang on a second, I'll just be back. Yeah, sorry for the disturbance and thanks for hanging around. So we'll just continue. Okay. So the next question is, this is again an easy question. Differential mode, right? So DM noise, current flows, power lines with dash directions. So does it flow in opposite direction or does it flow in parallel direction, that is in the same direction, right? Or is it in perpendicular direction, or does it flow in some random direction? So what is the answer? Differential mode noise will flow in the same direction or opposite direction?
Option A.
Yeah. So differential mode noise is always opposite, right? And that is something you want, right? Whatever is the forward current, it should be kind of the return current. Okay. Yeah. So the option is A, opposite. So the next question is again simple. Select all the components commonly found in an EMI filter circuit. Resistors, inductors, capacitors, diodes. So this is multiple select choice question, okay? So there can be more than one correct answer. So what is the correct answer? Or what are the correct answers for this? What are the components that are commonly found in an EMI circuit? Will, will it be resistor, inductor, capacitor, or diode? Sorry?
Inductor VSC.
Correct. So it will be inductors and capacitors. Okay. Fine. So I mean, these are all very simple questions only, right? Just the second question was kind of tricky. So the damping factor represents your quality factor, right? And both of them are inversely proportional. Okay. Damping factor is inversely proportional to quality factor. Okay. And the relation is actually epsilon is equal to 1 by 2q. This is your relation. Q is your quality factor. Okay. If you want, you can refer to your control notes, or even I think we studied this in first year networks, right, in BTech. So you can refer to those notes, how to find out the epsilon and quality factor and all. Okay, you would have studied that quality factor is equal to 1 by R root over L by C, right? I think you would have studied this particular expression also. Okay, fine. So if this is fine, we will move on to the next question, right? Okay. So the fifth question is also simple. EMI noise is measured through dash multimeter, oscilloscope, LISN. What is LISN? Can you tell what is LISN? Full form?
Line impedance stabilized network.
Correct. So what is the correct answer for this question?
LSC.
Correct. Okay, so EMI noise is measured through LISN. Okay, very easy question. So in low pass common mode filter, the reactive element employed is a dash. Capacitor, inductor, common mode choke. Or what is the answer for this? What is the reactive element that is employed in a common mode filter?
Common mode choke.
Correct. So, I mean, this is very simple, right? So, yeah, okay. So the next question would be, the equipment should operate normally even with interference from noise. The noise. So even if there is EMI noise, the equipment should operate normally, right? This is what you want. So this is known as dash. So electromagnetic interference, electromagnetic susceptibility, electromagnetic compatibility, or electromagnetic shielding. So what is the answer? So even if there is EMI noise, I want it to operate. Yeah. So the answer is C, how compatible it is, right? So option is C. Okay. So even if there is EMI, I want it to show good electromagnetic compatibility. Okay. Okay. So what is the main cause of conducted EMI in DC converters? Voltage fluctuations, circuit parasitics, discontinuous currents, PCB layout issues. So what is the answer for this? Conducted EMI. Okay, so the conducted EMI in DC option.
Voltage fluctuation.
No, actually the answer is for DC-DC converters, the main cause of conducted EMI is mostly discontinuous currents. Okay, that is on and multiple times the current for through the inductor, you want it to be ideally constant, right? Inductor is a constant current source. But what happens is your current is getting discontinuous. That is like the inductor kind of carries current, then it gradually it suddenly falls to zero, and then there is zero current and so on. So the reason is, yeah, this discontinuous currents. Okay, that is what causes conducted EMI. Okay. Conducted EMI is due to discontinuous currents. Okay. So we'll go to the next question. Which formula is used to calculate the required attenuation for an EMI filter? So I cannot write down all the formulae, but can you tell me what is the formula for attenuation? So it will be 20 log, right? Do you remember? It will be 20 log. Then it has to be V in minus whatever is the peak to peak ripple minus V max, right? That is, the answer would be the attenuation, right? The attenuation in dB, right, will be equal to 20 log V in minus the peak to peak ripple, peak to peak ripple divided by 1 microvolt minus V max. Okay, you can refer to this formula. It will just be V in minus the peak to peak ripple needs to be considered, and then yeah, so it is 20 log. Okay. Okay, so this question is easy. So EMI in SMPS is classified in two forms. So what are the two forms of EMI? So one is conducted and radiated. Differential and common mode. Low frequency and high frequency. Active and passive. So what is the answer for this?
Yeah.
Yeah, right. So this is the types of EMI. Differential and common mode is the type of noise and filter that you get. Okay. Okay. So if this is fine, right, we'll move on to the next. 11th question. Okay. What is the main function of an active EMI filter or AEF? To increase the voltage of the power supply, to sense noise and inject a cancellation signal, to convert AC to DC, and store MD. So what is the answer? What is the main function of an active EMI filter?
B.
Right. So it will sense the noise and accordingly it should inject a cancellation signal. Right. So related to this itself, which components are used to ensure system stability in AEF? So C comp, or comp. This is a multiple select option. Multiple answers can be correct. So what are the answers? So which components will ensure system stability? So to ensure system stability, the components are A and B, that is C comp and R comp. Okay. Okay, so I hope this is fine. So we will move ahead to the last question. Okay. So this will be the 13th problem. A major advantage of using active EMI filters is the reduction in overall dash of the filter components. So why do we go for active EMI filters? So is it the reduction in cost? Is it the reduction in size? Is it the reduction in weight? Or is it the reduction in complexity? So what is the answer?
Complexity.
So the answer is actually it is size. Okay, so
Okay.
so the point is like if you use active EMI filters, you know beforehand, like you kind of you need not design it for the worst case, right? Like that is you will know what is the um, uh, cancellation signal to be injected, and for that only that much signal only will be injected. Like you will not be having those bulky LNCs that you will design beforehand. Okay, so yeah, and answer is size. Obviously, if you go for size, then the weight will also decrease. Okay, but the option is only for a single option, so answer is only size. Okay, yeah, and yeah, so this is it for about all these questions, right? And we have already discussed questions on heat sinks and all. We have already solved problems also, so I'm not going into that right now. So yeah, so that is it. We have discussed questions on EMI today and questions also on power density. Okay, so I think this concludes the um, tutorial sessions. We have seen around 12 weeks. So thank you everyone for attending all these sessions, and yeah, so thank you to both of you. So you have attended almost all the sessions, right? Like Selvakumar sir and Anandi. So this concludes the session. So yeah, all the best.
Hall ticket
Thank you
was
for
done 2 weeks before. No?
Sorry, I didn't hear you, sir.
Hall ticket when it will come, sir? Maybe.
I'm not sure about those exam related stuff.
Okay.
Actually, I'm only a teaching assistant. So I will upload these slides, okay, and extra some questions are also there. I will probably type them and also upload them. You can go through them.
Okay, okay, okay.
Okay. So all of these are multiple choice questions and these are very easy. Okay.
Okay, sir.
So okay.
Okay, sir. Thank you, sir.
Okay.
Thank you for all your live sessions, sir.
Okay. Okay. Thanks a lot. And thank you to both of you for attending as well. You both have studied, I mean, you both have come almost in all the sessions.
Yes, sir.
Okay. So, yeah.
Sir,
Okay.
yeah.
I'll
Good
just
night.
stop recording
Good night.
and